Hi everyone. So together with Remy, we are going to present our work which propose alternative methods to train RNNs. So this method is inspired from a structure prediction technique called learning to search. So first of all, I will start by just doing a quick recap of what is an RNN. So as we have seen during Joshua's lecture, RNNs are models for sequential data, and they produce a sequence of hidden states by repeatedly applying the same operation on their input. And they do prediction by using their previous outputs. So in this work, we will focus on a specific architecture, which is the encoder-decoder framework, which has already been mentioned several times in the lectures. So these models are used to output a sequence given another sequence as input, such as, for example, for machine translation. In this framework, we have two RNNs. So the first one is called the encoder, and it processes the input sequence and transforms it into a vector, which is then fed to the second RNN called the decoder. The role of this second RNN is to predict the output sequence. One of the key properties is that each cell of the decoder has access to the whole input sequence through this initial state. Moreover, as we see in this drawing, every state of the decoder depends on the previous prediction. Here you can see that the W, for example, is given to the next cell to predict the word. So to train this model, we make use of the natural probabilistic interpretation of RNNs. Indeed, we can consider that the output of every cell of the RNN is a probability distribution over the values that YT can take, conditioned on the input and on the past decision. So this is the first equation on the slide. Thanks to this, we can use the chain rule to obtain the probability of any given output sequence conditioned on the given input sequence, X. Given this observation, we can use maximum likelihood to train RNNs, where the objective is just to maximize the probability of the ground truth input-output sequence pairs. So even if this framework is very nice, it comes with a number of non-limitations that Joshua mentioned during his lecture, and I will just recap three of them. So first, the likelihood is only a surrogate loss that might be different from the real metric you care about. So for example, you can care about edit distance or bluff score if you do machine translation. Second, it has also a problem that it has a all or nothing flavor, as mentioned this morning during the NLP lecture. Indeed, it's only trying to maximize the probability of the ground truth, and thus ignores the information that some candidate sequence can be pretty good, close to the ground truth, while others might be very bad. And finally, as mentioned by Joshua on Tuesday, it suffers from exposure bias. So since we use teacher forcing for doing maximum likelihood, we essentially always force the prediction path. But at test time, we don't have access to this ground truth path, and therefore when we deviate from it, we find ourselves in a situation we've never seen during training. So we don't really know what to do. And this can lead to compounding errors. So there have been some efforts in the literature to alleviate these problems, and some of these works notably use ideas from reinforcement learning. But here, instead, we cast the problems that are addressed by RNNs as a structure prediction task, and we look for ideas there. So let me just recall briefly what is structure prediction. So the goal of structure prediction is to learn a mapping between some input X and some structured outputs Y. So when I say outputs, structured outputs, it's because I assume that Y is made of interrelated parts that are often subject to constraints. So as illustrated here, this is notably the case for optical character recognition, where you might want to use the previous letter to predict the next ones. So the main difficulty with structured prediction is that you have an exponential number of possible outputs with respect to the input size. So in this example, if your alphabet size is of size k and L is the size of your word, you have k to the L possible words. So there exist standard approaches to tackle these challenges, such as structured SVM or conditional random fields, but here we focus on another one, which is called learning to search. So learning to search is based on the idea that instead of predicting the whole Y in one shot, you can make prediction one by one, where each prediction depends on the previous ones. So the core idea here is reduction, where you reduce the original complicated structured problem into easier sub-problems. In that case, we reduce down to what is called cost-sensitive classification, where the goal is to train a shared classifier that is going to predict every element yi of the output sequences. And cost-sensitive here simply means that instead of standard classification where we only have one target for a class, we will have one associated cost for each target, which allows to differentiate the possible decisions. Learning to search is backed up with some theoretical guarantees that ensure that if you are able to solve the simple problem, you will do well on the initial complicated problem. But most importantly, the method addresses the non-problems that we talk about for maximum likelihood. So now the question is, how do you train this shared classifier that I just talked about? So let's imagine we want some training signal for this cell which is in red here. So first, we will do a trajectory according to the current policy to get until this cell. Second, we will try every possible action or decision to determine their global structured cost. The first phase is called roll-in. Its role is to do some exploration for the network. The second phase is called rollout, and its role is to determine the cost of every action. Once you obtain this cost, you choose a loss and you can train the cell. We will come back in more details to this later in the talk. So as you might have already guessed, there are some strong links between this learning to search approach and the RNNs. And we really want to leverage this here. So indeed, both rely on decomposing structured tasks into some sequential predictions that are conditioned on the past decisions. So they both use the same shared classifier that is applied over and over to make the full prediction. But what ideas can we share between the two? Well, while RNNs have built-in roll-ins, for example, teacher forcing can be seen as a method of exploring the space, they don't really have the notion of rollouts, because the target is usually simply obtained by looking at the ground truth target. So the question is, can we adapt these ideas for RNNs? And now I will let Remy to answer this question.
Right, so how do we incorporate ideas from L2S in order to drive better training procedures for RNNs and hopefully avoid the problems that Jean-Baptiste talked about? So the one idea we want to focus on is to compute the cost of each token at every time step through the introduction of rollouts in the decoder RNN. And our hope is that we can leverage these costs in order to define better training losses that are closer to the test error. The algorithm is very simple. The first step is to compute the cost vectors with the roll-ins and the rollouts. The second step is to use these costs to derive a training loss. The third step is to take a gradient step associated with the loss. And finally, we repeat 1 through 3 until final convergence. So let me try to give a little bit more intuition into this whole roll-in, roll-out business. Here's an example on a single red cell again. And so you have the roll-in part where you start the exploration, you predict C, you feed it back, you predict O, you feed it back, and then you arrive at the cell where we want to compute the cost of outputting every possible token. Here the first one is M, so we start with this one, and then we use the rollout policy to finish the predicted sequence. And then we can compute the cost of M by applying the test error on the full predicted sequence. So here it's command. Right, so now we have a cost for M, and we do the same thing for N, and for O, and for everything else. And so in the end, we get one cost vector with one cost for each possible token. In this example, you can really see that the roll-in controls how the algorithm explores the search space, whereas the rollout determines how the costs are evaluated. All right, so here things get a little bit more complicated. What I've left out in the cost computation part, so the first step in the algorithm, is that there are several possible choices for both roll-in and rollout. For roll-in, you can use what's called a reference policy, and that means to always explore on the ground truth path. That's sort of the same as teacher forcing. On the other hand, you can use a learn policy, where you go where the model will guide you. And so this helps you alleviate the problem of exposure bias. For the rollout, you can decide to finish the sequence with a good known policy, because in some cases you have access to one, or you can rather decide to see where the current model would take you, and maybe this gives you costs that are a bit more realistic. Fortunately, exploring these different combinations has already been done in the traditional learning to search literature, so we already have some guidelines on what works best. And actually, a very neat point is that we can recover MLE as a special case of our method using a reference roll-in, a reference roll-out, and a specific loss. So this is a very useful sanity check. All right, so this was step one, computing the cost. And now onto step two. Once we have the cost, we have to actually pick the loss that will leverage them, that will leverage all of this information. And so we tried a bunch of different losses, including structured SVM loss and other traditional structured prediction loss, as well as losses that were more structurally similar to MLE. And so very basically in this case, we used the cost information to replace the ground truth target in the MLE objective by the best performing token at this step. And one final issue we have is that computing all of these costs gives us very meaningful information, but it's quite expensive. So it means doing a large number of forward passes. If we hope to apply SeaRNN to large-scale problems with big vocabulary size, we need to find a way to keep that computational cost under control. One of our leads is to use subsampling, so we only compute a subset of all costs. But then new questions arise. How much do we sample? And what do we sample according to? Right, so let me just recap why we believe SeaRNN can outperform MLE. First, we make use of the test error when we compute the cost. And so ultimately, we have it in our loss. Our loss is not exactly the same as a test error, but it's a lot closer than MLE, where you basically simply disregard the test error. This, in turn, allows us to leverage the structured information that the loss yields by comparing the cost for different tokens. Again, this is in contrast to MLE, which does not compare costs or make a distinction between a decent and a terrible candidate, because it's only concerned in maximizing the probability of the ground truth. Another advantage of our loss is that they bring global information, because we compute a cost on a full sequence, to the local level. And in the standard approach, you have local information at the local level. And in the reinforcement learning approaches, you have global information at the global level. The problem with the global information approaches is that their information is very, very sparse, and so often they cannot converge from scratch, and they require warm starting from a good MLE trained model. But enough talk, so let's see some numbers. We ran SeaRNN without sampling on 3 classical structured prediction tasks, which are OCR, text chunking, and spelling correction. So here are the results, where you have the MLE baseline, and then our performance with 2 different losses and 3 roll-in, roll-out combinations. And here you can see in red that we outperform MLE by 1 point in the case of OCR, where MLE is already pretty good, and by a more significant margin in the case of spelling, where MLE is actually pretty bad. Then we ran the sampling version of SeaRNN with only 10% of tokens on the OCR task and the sampling task. And we try 5 different sampling strategies. Right, so what do these experiments tell us? Well, first, and most importantly, we achieve significant improvements over the MLE baseline on all 3 tasks, which validates our idea that using training losses that are closer to the test error actually works. And as a matter of fact, the harder the task is, the bigger the improvements we see. So when the basic reference policy gets really bad, our method shines more. Going back to our policy decisions, roll in, roll out, we observe that in accordance to the theoretical results from learning to search, the best performing strategy is a learned roll in and a mixed roll out, which is reassuring. And the best performing loss, or at least the one that was easiest to optimize for, are actually those that are structurally close to MLE. Additionally, our global local losses enable us to train from scratch, contrary to the reinforcement learning approaches. And we argue that it's pretty important because it means we can explore wider regions of parameter space and potentially find better minimum. And finally, our sampling strategy works because we are able to maintain improvements at a fraction of the cost. Interestingly, sometimes we even have better improvements, although we don't yet have theory for that. Right. So while these results are promising, there are still a number of things that we want to do. The biggest one is to make SeaRNN scale to the point where it can handle problems with large vocabularies, such as machine translation. And we're currently following two main leads. The first one is to use smarter sampling strategies rather than the pretty basic ones we tried and that I haven't talked about yet. And these ideas include hierarchical sampling, where we first predict the class and then precise elements of the class, and that was mentioned in the talk this morning. And also curriculum sampling, where we change the amount of samples as the optimization goes along. So maybe we start with a lot of sampling, and then the further we go, the less sample we do. And the last possibility is, of course, trainable sampling, if we can pull that off. And our second main lead is to devise smarter methods of cost approximation rather than doing rollouts all the time. And this may bring us closer to the actor-critic model that was actually explored in the context of RNN here at Mila. Right, that's it for us, and we're happy to answer any questions right now. We'll be there on Saturday to answer even more. And if you're interested, please check out our paper on arXiv. Thanks.